Hello everybody, Dr. Powers here. We're going to look at some problems that'll help you with the confidence intervals and hypothesis testing on the population proportion. So we're going to use stuff in Excel to do this. There's other software, of course, that can do this. You could even do it by hand using a calculator, but we're going to use Excel. All right. So first off, here's a problem where we're asked to determine something. We want to determine if the proportion of smartphone owners who own an iPhone is different than 33%. So a simple random sample of smartphone owners is taken, and here's what we get. We got 45 out of a sample of 110. So what we're looking for is a decision. Is there enough evidence from this sample to conclude at a significance level of, well, since it's not specified, we'll say at a 5% significance level. So let's be formal about this, and we'll state what is the null and the alternative hypotheses. The null hypothesis is that the proportion in the population is equal to 0.33. That's to say that the proportion of iPhone users is exactly 33%. And the alternative is that it is different than 33%. You're always going to have equality as part of your null hypothesis. I'm just going to say not equal to 0.33 just for brevity. But if you want to be a little bit more professional, you want to use the not equals sign. I'm more concerned right now with doing the math. Okay, so we are going to calculate a test statistic, and the way we do that is first we're going to calculate our p hat, and that is going to be the number of iPhone users from the population from the sample divided by the sample size. So 45 out of 110. It certainly seems like it's higher than 33%. The question that a hypothesis test is really getting at is, based on this sample size, is this proportion, is it higher than 33% enough to, based on the sample size, that we can conclude it's due to a difference in the population proportion and not just due to sampling error, right? Because it's certainly possible that we just happen to get lucky and sample a bunch of iPhone users out of the population, even though only 33% of them use iPhones. Or maybe the true proportion actually really is different than 33%. Okay, so we're going to calculate our z statistic. Now we're going to use the z statistic because we're going to approximate the distribution, the sampling distribution of p hat using a normal distribution, because that's kind of what you do in a intro stats course. The sample size is large enough such that we got 45 iPhone users out of our sample, and thus more than the rule of thumb that often we use is you should have at least 10 quote-unquote successes and 10 failures out of your sample. And there's 45, and there's going to be 65 I guess other kinds of phone users out of this sample. So it's a large enough sample that it should be approximately normally distributed, like a bell curve kind of a shape. Now the z-stat is calculated as the sample, the p hat minus the null proportion, 0.33. And we're going to divide that by the square root, SQRT, the square root of p hat from the null hypothesis. Actually, I'm going to type it in, 0.33 times 1 minus 0.33. This is how you calculate this, the standard error. And then I divide it by the sample size of 110. That is the denominator. So it's the null proportion times 1 minus the null proportion divided by the sample size, the square root of that whole thing. Here's my z statistic. To calculate p-value, now here this is a two-tailed test because my alternative hypothesis is that the the proportion is just not equal to 0.33. So I'm going to, for my p-value, I'm going to calculate norm dot dist, parentheses, I'm going to calculate, let's see, we're going to have to, I want to find the, if I do the negative of this, that'll find the probability in the lower tail. And then I'm going to give it a mean of 0 and a standard deviation of 1, and I'm going to say true for cumulative. So what I'm trying to calculate here is well, let me show you in a picture. So this is the picture I'm trying to calculate. I want to calculate the probability out in these two tails. Now, what I was just looking at here was the probability out below. Let me show you again. This formula, this is calculating the probability in the lower tail, right? The cumulative probability up until you get to negative 1.76. I actually have to multiply this times 2 because there's two tails in this test, so I have to double that. So in fact, the p-value is twice that number that I just quickly calculated by just the one tail, 0.077. This p-value tells you if the sample proportion, if the population proportion really is 33%, then we have about a 7, almost 8% chance that a sample of 110 people will result in 45 or more, or 45 iPhone users, or something like that. A sample proportion that's this different or more different than 33%. 8% is not low enough for us to discount the null hypothesis. So we would say there is not sufficient. Okay, so there's not sufficient evidence from the sample data to conclude that the population proportion is different than 33% at a significance level of 5%. I should point that out. Right? In this case, we do not reject the null hypothesis. Okay, so now with bags of Cheerios, they are labeled as 16 ounces. Let's suppose we're working in a Cheerios factory. All right, we take a sample of 99 bags of Cheerios, and the manager wants to demonstrate or prove or conclude that fewer than 10% of the bags weigh less than 15.5 ounces. Is there enough evidence to conclude at a significance level of 0.05 that the proportion of light bags, so when I say light bags is weighing less than 15.5 ounces, is below 10%? Now I'm talking about the population proportion, not the sample proportion. We know what the sample proportion is. It's easy to calculate. Actually, here's how we're going to start by calculating that. First, we're going to get the number of light bags in the sample. That's going to be used, we're going to use the COUNTIF formula. So COUNTIF, one word, parenthesis. I select this whole range, put a comma, and my criteria is double quote, less than 15.5, double quote, close the parentheses. That's going to count all of the bags that are less than 15.5. There's 3 of them. Okay, and sample size, of course, is, I'm just going to put in the 99. Now let's calculate the sample proportion, p hat. That's, of course, 3 out of 99. That's pretty low. Is it low enough, though, that we can make our conclusion? Well, let's formalize the hypothesis test. The null hypothesis is that p is equal to 0.10. The alternative is that p is less than 0.10. All right? So my z-stat, as before, is going to be found by taking the difference, my sample proportion minus the null proportion of 0.10 divided by the square root of 0.10 times 1 minus 0.10, divided by the sample size of 99. Remember, I divide by the square root of the null p times 1 minus the null p over the sample size. that whole thing is square rooted, and that whole thing is in the denominator. Okay, my z-stat is pretty low. I'm going to calculate, since I'm doing a lower tail test, I want to calculate the probability in the lower tail. So that my p-value is going to, be norm.dist. I take this value, comma, mean of 0, standard deviation of 1, and the cumulative is going to be true. This will calculate the lower tail probability. If I wanted to find the upper tail probability, I would need to do 1 minus this number. Okay, so this is good. My p-value is 0.01. Because the p-value is less than 0.05, we reject. Yep, so there is, we reject the null hypothesis. There is strong evidence from our sample that the proportion of light bags is below 10%. So if the proportion of light bags were actually 10%, there would be only a 1% chance, roughly, that we could sample 99 bags and get results kind of like this. It's far more plausible that the true proportion is lower than 10%. That's the idea of this conclusion that we've made. All right, now we're going to calculate a confidence interval. In a poll of 100 individuals, 425 said they love dogs. We want to find a 95% confidence interval for the proportion of dog lovers in the population. So let's calculate my dog lovers. There's 425. Sample size is 1,000. Okay, p hat. The sample proportion, easy enough to calculate, right? 425 divided by 1,000. Now we want to find the margin of error. I'm going to calculate all of these parts. So z star is a critical z value. And this is the critical z value for a 95% confidence interval. Actually, let's put it here. My confidence level is going to be 0.95, right? Take a step back, and the significance level is going to be useful. The corresponding significance level is 1 minus this 0.95. Okay, so my z star is found by doing norm.inv, the inverse. Now it's going to be 1 minus the significance level over 2. Okay, so the idea is I want to, if you've got 95% probability in the middle of the distribution, there's a 5% split evenly among the two tails, right? Lower tail is going to have 2.5%, the upper tail has 2.5%. So I want to find the cutoff for the top 2.5%, which is the same as the bottom 97.5%. That's what this 1 minus 0.05 over 2 gets me. That's 0.975. I give it the mean of 0 and the standard deviation of 1, and we get our z star, 1.96. That should sound familiar. It's from the empirical rule. Standard error can be calculated by its p hat. It's the square root of p hat times 1 minus p hat divided by the sample size. Now for a confidence interval, the standard error is based on my sample proportion, because in a confidence interval, I don't have any null hypothesis. I'm not making any hypothesis. I'm just doing an estimation. For a hypothesis problem, I'm assuming when I'm calculating the sampling distribution of p hat, I assume the null hypothesis were true, and then that leads me to a standard error based on the proportion from the null hypothesis. So I just want to make that note. The standard error for a confidence interval is based only on p hat, my sample proportion. For a hypothesis test, my standard error is based on the null proportion. That's a big difference, and it can give you very different answers if you screw it up. All right, so now finally my margin of error. Margin of error. This is going to be my z star times my standard error. And so my lower bound and upper bound is going to be my p hat minus the margin of error, the p hat plus. All right, so then we conclude this by saying we're 95% confident that the proportion of dog owners in the population is between 39.43% and 45.46 or 56%. Okay, because that's what our lower and upper bounds. Of course, there's a 5% chance that our confidence interval doesn't capture the population proportion. And there's a 95% chance that my confidence interval does correctly capture the population proportion. Remember, the population proportion is not a random variable that has a distribution. The population proportion is fixed. It's our confidence interval based on a random sample that's treated as a random variable, right, with a distribution. If we had sampled 1,000 different people, we would have got a different confidence interval, right? So, yeah, that's how we calculate a confidence interval. Now, we can also use a confidence.norm function. I give it alpha, give it the standard deviation, which is, this isn't so easy. I have to give it the square root of p hat times 1 minus p hat. And then I give it the sample size of 1,000. This should also calculate my margin of error for me. So you can calculate your margin of error using the confidence.norm. You have to give it the standard deviation parameter in your function. It has to be the square root of p hat times 1 minus p hat. That's what you would give it, and it'll calculate the margin of error for you if you want to use that. It saves a little bit of time, but not a ton. Of course, if you use other software, it's going to be way easier. A poll will be conducted to estimate the proportion of people who can smell asparagus pea. We aim to calculate a 98% confidence interval with a margin of error of 2.14 percentage points. So that's our goal. Now the first question is, if we had a prior estimate of 40% of the population proportion, then how many individuals should we sample? Right, so the sample size is calculated as the rounding up of okay, so it's our p times 1 minus p times z squared over the margin of error squared. This is the formula. I'll try to help you make sense of that, but let's put all this stuff. So our p estimate is 0.40. All right, our z star is based on a 98% confidence interval. So this is going to be z.in or norm.inv. I'm going to put in the 1 minus 0.02 divided by 2. Since I'm doing a 98% confidence interval, the corresponding significance level is 2%, right, or 0.02. And so to find the z star, I'm going to use 1 minus that 0.02 divided by 2. Really, there's just 1% in each tail. The mean of 0 and a standard deviation of 1. That's my z star. My margin of error that I want is going to be 0.0214. I have to put it into decimal. I can't use the 2.14. It would be very messed up. So my sample size that we need is going to be, I'm going to use the ceiling dot math function, okay, and then I'm going that'll round up. So it's going to be p times 1 minus p divided times z star squared divided by my margin of error squared. That's going to be my answer. 2,837 individuals are needed for me to achieve this. Okay? If I were to now, if the if I don't have any sort of estimate as far as what the estimate is, what the proportion is, what I'm going to use for part B, for the P estimate, I'll use 0.5, because you always plug 0.5 into the formula if you don't have a prior estimate, because that's the widest the confidence interval can get. The margin of error, that's the widest the margin of error will get, is if your sample proportion is 0.5. Once it gets to be larger than 0.5 or smaller than 0.5, then the margin of error starts shrinking. So we use 0.5 to be overly cautious. And this other stuff is the same, so I'm going to just copy this stuff over. Okay, so I'm going to actually just use the same formula, see what I get. If I use 0.5 instead, 2,955 individuals will get me a confidence interval with a margin of error that's at most 2.14 percentage points. It may be lower than that, but this is the most I would need to sample in order to hit my target. And I might do better, but yeah. I mean, one thing that you can kind of do in practice is, if you don't have a prior estimate, you can sort of sample until you, and you can sort of calculate your sample proportion as you go along, and you could either, well, you can kind of stop sample, like you could do like an initial sample to get an estimate, and then you can plan out the rest of your sampling based on the initial sample. But anyway, that's the formula for calculating sample size. Yeah. All right, a survey of 80 college students asks whether they drink coffee in the morning. We want to find a 95% confidence interval for the proportion of morning coffee drinkers among all college students. So, assuming that this is a good random sample, we want to figure this out. So let's do this thing. Now we've got the I'll say the number of coffee from the sample. That's going to be found using the count function. I'll use count if. I'm going to just count if the person said yes. So I'm going to select this whole batch of this whole range, comma, and in parentheses I put yes, lowercase, exact match. 56 was the match, and I'm going to say count. Of course, I was told that there was 80, but let's just pretend I don't even know that. Oops, count. I wanted that to actually be over here. Count. Oh, it would only count numbers? Oh, count A, the number of cells that are not empty. Okay. Count by itself only counts cells that have numbers in them. 80, yeah. So this is n, sample size. P hat is going to be 56 divided by 80. My significance level, I'll put it here at 0.05. That corresponds with the 95% confidence interval. Z star is my, you know what I'm going to do? Since I'm running low on room, I'm going to just shrink this down a tiny bit so that I have a little bit more space. Okay, Z star is norm dot inv, parenthesis, 1 minus that significance level divided by 2 with a distribution with a mean of 0 and a standard deviation of 1. Okay, and then we want to, the margin of error is going to be calculated as, it's going to be my Z star times the standard error, square root of P hat times 1 minus P hat divided by the sample size. Okay, and so my confidence interval lower bound is going to be my P hat minus this margin of error. The confidence interval upper bound, that's the P hat plus the margin of error. So I would say so my conclusion would be that I can be 95% confident that somewhere between 60 and 80% of college students begin the day with a steaming steaming hot cup of joe. Yeah, so this is my interpretation of this confidence interval. And as I mentioned before, you can use the confidence dot norm function given the significance level, the standard error deviation, which is calculated as the square root of my p hat times 1 minus p hat in parentheses, so that I don't mess up the multiplication, and then my sample size of 80. This will also calculate this margin of error for me, so you can use that as well. Well, this should hopefully prepare you for all of the challenge activities for this module, and I hope you do really well. That's it for me. See you later. Bye.